In this video, we're going to look at the divergence theorem. And the divergence theorem relates the double integral over a closed surface to the triple integral over the volume contained by the surface. So in other words, the volume inside that surface. Now again, to apply this theorem, the surface must be closed. And the divergence theorem says if you're asked to do an integral like this, is double integral f dot ds, that's equivalent to doing the triple integral where we have the divergence of f. You recall this is the divergence of f. And again, this is over the surface. This is over the volume inside the surface. That's what's represented by that E. So sometimes you're asked to do this, or equivalently, you could be asked to do this surface integral. Remember, these two are the same. So if you have to do this or this, you can apply the divergence theorem instead. So let's take a look at an example. So suppose you're given this problem. Use the divergence theorem to evaluate this integral, where a vector field is given this way. And S is a surface enclosed by the sphere. Obviously, that's the equation of a sphere. And N is the outward normal to that surface. Now recall, if you have something like a sphere and something's an outward normal, that would be pointing out from the center of the sphere. And that would be positive orientation. And so we want to apply our theorem. So again, instead of doing this integral, we're going to do, so instead of doing this, we're going to do this. So we're going to need the divergence of f. So let's calculate that. And to recall that this operator is represented by this. And so let's do this dot product. So this is saying we're going to apply this to this term here. And when we take the derivative of this term with respect to x, that's going to leave us z squared plus 0, there's no x's here, plus 0, no x's here. Then next, we're going to take the partial with respect to y of this term. That's going to be 0. And then this is going to be what? That's going to be the 3 comes forward. Those will cancel. That'll be y squared. And that'll be 0. Finally, we're going to take the derivative of this last term with respect to z. That's 0. That's going to be x squared. And we can make it look like our familiar, which is a little bit more familiar to us. We can rewrite that as x squared, y squared, z squared, like this. And so the other thing to keep in mind, again, this is the sphere of radius 3. So you could think of this as being the same as 3 squared. So we have a sphere radius 3. So again, let's apply our theorem. And let me just write this again, just to help remind ourselves what we're doing here. So once again, instead of doing this integral, we're doing this one over the volume. And then we've taken the divergence. Like this. And then finally, this looks like something that would be good for a spherical coordinates. And of course, also the fact that we're integrating over a sphere, we're integrating, remember, if this was a surface, we're integrating over the volume within that surface. And so that's a sphere of radius 3. So we can convert to spherical coordinates. And so we're going to go from rho equals 0 to rho equals 3. And then from theta equals 0 to theta pi over 2. Then the radius, the rho, the phi will go from 0 to pi. You recall the phi, to get a sphere, phi just goes from 0 to pi. So again, make your substitution. Remember, in spherical coordinates, x squared, y squared, z squared is rho squared. And then include your Jacobian, which is going to be rho squared sine phi d rho d theta d phi, like this. And so let's go ahead and carry out the integration here. Notice that this is rho to the 4th. So when we integrate that, we'll get rho to the 5th over 5. And that's going to be evaluated from 0 to 3 in this phi. And we'll be left with d theta d phi, like this. Then now here, again, we'll put our 3 in. So it'll be like 3 to the 5th over 5. And so we'll put that in, and then the lower bound will be 0. So we'll put those numbers in. And let me save a step and then do the next integration. We'll integrate with respect to theta. And so that's sine phi d phi. And this theta will be evaluated from 0 to 2 pi. Then we'll put 2 pi in here. And minus the lower bound, which is 0, so that'll go away. Now we'll integrate with respect to phi. And let me just recopy these numbers down here. And we'll integrate with respect to phi. The sign will go to a negative cosine. evaluate from 0 to pi. And then what we're going to have will be, this will end up being, of course, this will all stay here. And then the cosine of pi is a -1. And then minus the lower bound. And we'll have a negative here. And then the cosine of 0 is a +1. So this is going to be 2. So, because that's going to be a +1 plus a +1, that'll be 2. So we'll end up with 3 to the 5th 4 pi divided by 5. And then if you put this in your calculator, you get 194.4 pi. Like that. In this video, we're going to look at this problem here. We're asked to evaluate this surface integral where the vector field is given this way, -4x plus 3yz, y minus x, 8z plus e to the xy. And S is the surface of the cylinder x squared plus z squared is equal to 16, enclosed between the planes y equal 1 to y equal 5. So let's take a look at that. So once again, we're going to apply the divergence theorem. And so once again, recall we're going to need the divergence. And actually, it might be interesting first to maybe draw the picture, or at least get a general feel what the picture might look like. And so you'd have like this cylinder. So you can see it has x squared plus z squared 16. So it's like a circle in the xy plane, but since y isn't there, you get the circles repeated. So we pretty much have a cylinder that goes kind of out this way. That's a bad drawing. Sort of out this way, starting at y equal 1 out to y equal 5. And again, this is x, y, and z. And again, this cylinder is x squared plus z squared equal 4 squared. So once again, notice it's a closed surface because the cylinder is on the side. Then at the ends are the two planes. I didn't really show them here, but there's like be a plane here at y equal 5, plane here at y equal 1. So again, let's apply the divergence theorem. First, let's do the divergence. divergence of f. Once again, remember what that is. That's d dx, d dy, d dz, dotted with f, like this. So again, this is going to be the derivative of the first component with respect to x, and that's going to be minus 4 plus 0. Then derivative of this with respect to y, that's going to be 1 plus 0. And then derivative of this is going to be 8 time derivative, that's going to be 0. So we're going to have what? 9 minus 4 looks like 5. So let's go ahead and apply the divergence theorem. Remember, you don't always have to write all these steps up. I'm just kind of writing that to remind us what we're doing. We're asked to do this integral, but we're going to do the triple integral of the volume inside this surface S. And we did this over here. Like this. And now let's factor out the 5. We'll have like a 5 out front here. So now we have the triple integral over a volume and no function in front here. So if you have a triple integral over a volume, that's simply going to be the volume of the object. Just like, did you recall, if we had a double integral dA, once again, where there's no function in front, no variables in front, that could be simplified to be the area. So here, if you have a triple integral dV, that's simply going to be the volume. Now, sometimes we don't know the volume. We have to actually integrate this to calculate it. But so let's say this is the volume. And basically, it's a volume of this cylinder we have up here. And so let's actually do this. So we're going to have the 5. And then the volume here is going to be what, like pi r squared. That's going to be like the area of the circle times the height, which is going to be 5 minus 1, which is going to be 4. And actually, the radius, we know the radius. So let me put that in. That was 4 squared like this. So it's going to be 4 squared times 4 cubed. So it looks like it's going to be 5 times 4 cubed pi. So again, what we had right here, again, this would be the volume of the cylinder. And then we got this, and we put that in the calculator. I got 320 pi. Let's take a look at this example. We're asked to find this surface integral. and this is the vector field F. And in this case, N is the outward normal to the surface. So again, we can assume like it's positive orientation. S is a surface of the paraboloid z equal x squared plus y squared, which is inside the cylinder. X squared plus y squared is 9. And the surface includes the cover. Now, by having the cover makes it a closed surface, so we can apply the divergence theorem. And so again, just to recall, if we're asked to do this or this, now in this case, we're asked to do this integral over the surface. Instead, we could do the triple integral over the volume enclosed by that surface. And so we're going to do that. And as usual, it might help to get an idea of what the surface and volume look like. So we'll have, say, this paraboloid. Like this. Z X. Y like this. But then it's inside of the cylinder. Something like this. So again, so I can look ahead. It looks like we're probably going to end up using polar / cylindrical coordinates. So basically what we have then, so our surface here is z equal x squared plus y squared. And of course, if we change the polar / cylindrical, that's going to be z equal r squared. And then we're eventually going to need, what's down here in the domain. So like I could imagine we're going to integrate over this volume here. And then this is going to project down onto the xy plane. And so let's just take a look at that. And this cylinder's radius 3. Like that. That's, I think, is eventually going to be our domain. So once again, we're going to use the divergence theorem. And so we're going to need the divergence. So let's sort of do this out here real quickly. We're pretty used to doing it now. So the divergence of f will be the derivative of this with respect to x, which is 3. Derivative of this with respect to y, which is -7. Derivative of this with respect to z is -2. Because we do this with respect to x, this all disappears. This disappears, this disappears. And so we have 3 -7 -2. That's going to be minus 9 plus 3. It's going to be minus 6. And so let's apply the divergence theorem. And remember, we're going to do the triple integral of the divergence of f dv, which is going to be equal to this. So mainly, we're going to go from, we're inside this paraboloid and going to go up to this z equal 5. So again, you can imagine starting at the bottom here, z will start at the bottom. And at the bottom here, like, so imagine yourself standing inside here. You're going to be standing on this x squared plus y squared, which in polar cylindrical, it's r squared. So your lower bound is going to be r squared. And your upper bound is going to be this upper surface here, z equal 5. Like this. And then if, again, doing polar, we're going to go from r equals 0 to r equal 2 pi. Excuse me. R equal 3 is the radius. Because remember, this cylinder here was x squared plus y squared equal 9, or 3 squared. So from r equals 0, r equals 3. And then finally, our theta will go 0 to 2 pi. And we have our divergence here, which is minus 6. And then it's going to be r dz dr d theta. Always remember, when you switch to polar or cylindrical, you have to include the Jacobian r. So now we can just go ahead and integrate this. Of course, you can bring that minus 6 out front. And this is just going to be, we integrate this with respect to z, we'll just have z r dr d theta. And z was evaluated from z equal r squared to z equal 5. And this other one, 0 to 3, 0 to 2 pi. And then put the values in here. Five minus the lower bound here, which is r squared, and then r dr d theta. So it's minus 6. And we're going to have to multiply this r in at some point here. So let's multiply this in. 5r minus r cubed dr d theta 0, 3, 0, 2 pi. Then integrate with respect to r. That'll give us 5 r squared over 2 minus r to the 4th over 4. Those will be evaluated from 0 to 3. So it'll be minus 6. D theta. So this would be 5, 3 squared over 2 minus 3 to the 4th over 4. And then the lower bound to be 0. So that'll disappear. Then we have d theta, like this. And then integrate once again. And when we integrate that last time, a theta here, and that'll be minus 6. And then a theta was evaluated from 0 to 2 pi. Put the 2 pi in like that. And when I put that in my calculator, I got negative 27 pi. So once again, instead of integrating over this surface, the paraboloid and the top, we integrated over the volume in there. And again, if you imagine yourself standing in the positive z direction, your feet will be starting on the paraboloid x squared plus y squared, and your head will be pointing up towards the upper surface, z equal 5 in this case. And so our bounds are going to be from this up to z equal 5. And again, this was originally, so we'd be starting at x squared plus y squared. But if we look ahead and see ourselves changing the polar cylindrical, x squared plus y squared is r squared. So our lower bound is r squared, our upper bound is equal 5. And then this region projects onto the xy plane as a circle of radius 3. And so our bounds are 0 to 3, 0 to 2 pi, and then just carry out the integration. And let me make this one just a little neater. Like that.